All right, so without further ado, let's get the show on the road. We're going to start things off with this strong morning session. We have a panel lined up to discuss nuclear thermal propulsion. Now that's the short title. The long title is Reducing Transit Time, the Wonders, Opportunities, and Challenges of Nuclear Thermal Propulsion for Human and Scientific Exploration. Our all-day sponsor today is Dynetics. And let's welcome our moderator, Dave Burns. Dave is the director of the Science and Technology Office at the NASA Marshall Space Flight Center. Welcome, Dave and panel.
Thank you very much. There's something inherently odd about being a moderator for a nuclear propulsion discussion. It does set the bar low. Basically, if I perform better than a block of crap, I've done my job. So I am looking forward to today's session. The three reasons why NASA is interested in nuclear propulsion. The first is for deep space human exploration. Space is a dangerous place. Not having gravity for long periods of time is rough on the human body. Being exposed to radiation is also very dangerous. Speed has its own value, and nuclear propulsion brings that. Science is the second reason that we're interested in nuclear propulsion. There's some science missions, particularly to the outer solar system, where nuclear propulsion really enables the science to be gathered while the PI is still in the field. If we have missions, one of the missions that was proposed was a 1,000 AU mission. You can imagine trying to do that without nuclear propulsion. That gets really difficult. So for us to be able to do science and bring enough power with us to be successful in conducting that science, nuclear propulsion offers an opportunity for that. And then third is commerce. Commerce is one of the key reasons why NASA was invented in the first place. And to enable commerce to extend beyond low Earth orbit, nuclear propulsion is one of the ways that opens the door for that to happen. So we're excited about this. NASA's had a long history in here, and we're very interested in hearing our presenters speak today. Before we go into this presentation, I thought I would give just a quick discussion on NTP versus NEP. NTP is nuclear thermal propulsion. What you do is you take a working fluid, liquid hydrogen, for example, you heat it up in an open reactor, and that adds energy to the hydrogen atoms, and that gives you your thrust. NTP has a very high thrust and a much better specific impulse than you would get with a chemical engine, and I'll let our panel talk about that some. In EP, you have a nuclear reactor that's tied to an electric propulsion system. You can also run an electric propulsion system with solar, but once you get past, say, the orbit of Mars or the asteroid belt, it's difficult to get the kind of light and the energy you need. So using something like NEP, where you have a nuclear reactor tied to the electric propulsion system, makes a lot of sense. NEP has lower thrust, but can operate for a very long period of time and has even more specific impulse than you get with NTP. So when you look at the architecture for exploring our solar system, both with humans and science payloads, there's a place for both of them. And today we're going to be talking primarily about NTP, which is nuclear thermal propulsion. All right, let me jump straight in. Our first presenter is Ethan Chaleff from UltraSafe Nuclear Technology Advanced Technology Division. Ethan is a PhD nuclear engineer with a background in advanced reactors for space and terrestrial power. He has been a NASA fellow through Glenn Research Center, a Department of Energy fellow at The Ohio State University, and a visiting fellow at Oak Ridge National Laboratory. Ethan joined UltraSafe Nuclear in 2020 as a mechanical engineer manager. He is currently the program manager for nuclear thermal propulsion at UltraSafe Nuclear, overseeing NASA and DoD contracts, as well as managing USNC's internal research and development into NTP. So thank you, Ethan.
Thank you, Dave. And thank you for the moderator pun. I think that's maybe underappreciated by some in the room, but not probably the panel. Yeah, so as Dave mentioned, my name is Ethan Chaleff. I'm here on behalf of UltraSafe Nuclear. We're, I think, relative to the rest of the panel, a relatively smaller company and newer entrant into the field, but we're doing big things fast. So a little bit of introduction about what UltraSafe Nuclear is. So we're, again, probably bigger than you've last heard of us because we've continued to grow, over 250 employees worldwide, primarily based in the United States. Our headquarters in Seattle, Washington, but facilities around the world. So the kind of core technology of UltraSafe Nuclear is FCM fuel. This is a terrestrial reactor fuel that's not directly relevant to NTP, but it's really kind of the heart of the company and what allowed us to get going and get started and grow. So ultra safe nuclear is based around this technology called FCM fuel, or fully ceramic microencapsulated fuel. It's the technology we own the most IP about, and that's kind of familiar. If you're familiar with the advanced reactors, it's similar to graphite compact fuel, but a number of key advantages, including increased fission product retention and a zero stress manufacturing process that prevents compacting particles when you form compacts. We just opened our pilot fuel manufacturing facility, which is working on producing its first fuel for both qualification and testing purposes. And that opened at Oak Ridge National Lab, or near Oak Ridge National Lab in the East Tennessee Technology Park. You can see that picture down there, and that. Nuclear thermal propulsion, ultra safe nuclear. Why is a ceramic fuel company working on nuclear thermal propulsion? Well, our long-term goal is to be the supplier of NTP fuel and also reactors to NASA, DoD, and eventual commercial uses of NTP. Our founders have long been really invested in NTP and really want to make it a core part of the company. It's currently the second largest program at the company after our terrestrial reactor program. Internally, we're very involved in the NASA program, as well as our internal fuel development R&D that continues to go on internal funds for now. As well as developing material testing capability and working on delivering particle fuel to NASA early next quarter. We're involved in a limited basis on the Draco program and working to explore potential future uses of NTP with a variety of customers, both within the U.S. government and commercial industry. And as part of our team, we're forming strong relationships and continue to work with Blue Origin, as well as Framatome, which is a traditional nuclear fuel supplier, GE Hitachi, and Materion Corporation. So a little bit about our kind of system concept, and I apologize for not necessarily going into as much detail as I think Russ will hopefully go into about what NTP is and what value it provides and how it gets to Mars. But as a design company, focus on what we see as some of the key technology attributes that we can develop and push forward as part of NASA's program and as well as other programs. So we kind of internally, jokingly, or a little bit tongue-in-cheek, call it PADME, a very space-focused company, which is a good backronym that I still am in awe of every time I see it. But Power Adjusted Demonstration Mars Engine, as you know, NASA's working on a reduced scale demonstration engine to prove the viability of the technology, and that really drives a lot of our technology choices. So a beryllium block and tie moderator. One of the key attributes of beryllium is we know all the key attributes of beryllium, and so that's really a strong benefit when you're doing a development program, is reducing the development burden on technology. The other important thing is, we talk a lot about 20% enriched fuel, but we've made the down selection to use 9.9% enriched fuel. And the key distinction there is being able to use existing fuel fabrication facilities without going through modification of a Cat 1 facility or developing a new Cat 2 facility, none of which are currently licensed. So it obviously challenges the design. The original ones were 95% enriched uranium. So 9.9% certainly is a penalty there, but again, the focus is on getting to Mars soon, and that's kind of the theme of USNC's participation. Is the way you get there faster is getting there sooner, or getting started sooner. And again, we've worked on advanced fuel technology, not just on the materials I'll talk about in a little bit, but also kind of internal geometries to reduce as much as possible the operating temperature of the fuel to where it can reach the outlet temperatures needed for the kind of 900-second ISP targets that we commonly talk about. Yeah, so as I mentioned a couple slides ago, we I think had a reputation, for those of you, hopefully I'm not reinforcing this for those of you who don't know us, but for those of you who have known us for a while, as a paper reactor company, which is true, except nothing on paper anymore, it's all digital. But other than that, so we recently commissioned our fuel facility after commissioning a building in East Tennessee Technology Park 15 months ago, and that facility is already making surrogate runs to commission pilot lines of the exact fuel fabrication components that will be part of our larger eventual commercial factory. So that's very exciting, and currently working on both producing silicon carbide TRISO for commercial fuel fabrication, as well as a uranium nitride coated TRISO or TRISO-like particle with ZRC instead of silicon carbide under a NASA-funded effort, and we're very excited about that. And really kind of the theme of our fuel effort is leveraging advanced manufacturing, right? In the 70s, NERVA had HEU. We don't have HEU. We need to be more clever about the materials we do put in there and how they're arranged. in order to survive the challenging conditions of NTP. So if you've thought about NEP or if you've thought about NTP, there's a lot of system challenges. There's a lot of complex things going on getting to Mars, but really the heart of NTP is fuel. If it weren't for fuel, it would have been done 7 years ago, and that's everything we'd use. But the fuel is hard. It's not just about the temperatures. It's also about the very intense thermal gradients and thermal transients, both in time and space, that operating an NTP reactor puts on the fuel. And there's very little demonstration that we can go off in recent successes with technologies, materials, and geometries that are proven to work. And so there's a lot of work to do in parallel with the program, and that's really drives the philosophy of getting to test as soon as possible, so we can break things faster, learn from it, and go back. So as I kind of mentioned, ultra-safe nuclear, our position is the fastest way to get to Mars isn't to go to slightly higher ISP. It's to take a first step so you're actually walking. And as the program matures and as kind of the panelists on the stage are working towards different concepts, the focus, I think, has to be on how do we get something we can test, not what do we want to fly, because there are a lot of constraints in the operating environment. The first NTP reactor will not be the nth NTP reactor. There has to be a first step to recreate the technology and the supply base for NTP in this country to be able to kind of get to where we want to go and where the technology can go down the line. Again, so fuel performance, the ability to test and get useful data on the ground, all of those things are not just prerequisites for flight. They should really be planned as a development step on the way to flight. And so we've advocated internally and are working with the program to understand what that would mean, stepping back a little bit. And I think there's a lot of agreement on that from maybe some of the thresholds that were set towards reducing some of the key drivers of cost and schedule for a ground demonstration to be able to execute on an NTP demonstration at a significantly reduced cost to the program. And again, we talked about deep space, we talked about human missions to Mars, but those are some slightly more challenging specifications. And so, a lot of recent talk about cislunar architectures really provides a lot of benefit to the technology where cislunar NTP can provide a performance advantage over chemical while reducing a lot of the system design and challenge that complicates an eventual mission. And so again, testing something sooner will teach us more than designing something better. Cislunar and science missions are critical for providing mission pull. How much water do astronauts need for a human Mars mission? Maybe someone here probably knows that very well, but presumably to me, it seems a little bit, uncertain on some of the technology aspects that drive mass. And so, a Mars mission, any Mars mission is a long way away and lacks technology pull to make key design just down selections on the performance of an engine. And so, between vehicle design, mission planning, et cetera. And so, a near-term use of NTP, near-term use, not just a demonstration, not just making hot hydrogen in space, but a near-term use of NTP where it can provide a comparative advantage would be a strong mission pull that, we're excited to explore and is one of the things we're working on over the next year in terms of identifying what that reference mission could be. And again, it's, I think, also worth, we talk pretty exclusively about liquid hydrogen, but ongoing studies that we've done that others continue to look at of primarily ammonia as a propellant, where yes, you lose the ISP, but the increased storage density and decreased tank mass of your propellant storage, complexity of cryogenic fluid management, which no comment on, but is a prerequisite for flight use. And so if you can remove that burden and still have an efficient system, then I think that would be very important. And lastly, emphasizing that, cislunar near Earth implications, or at least, from our perspective, where the commercial uses of NTP are in terms of science, deep space, exploring Jupiter's moons, that's very exciting, but kind of commercial revenue driven applications, as Dave mentioned, which is the impetus of NASA to develop this technology, are why, commercial and private companies are invested in NTP. So what's next for us? We're looking forward to there's an extension to the phase 1 design contract that we're currently working under for NASA. And we're excited about that as an opportune moment to really help refine and set the direction. There's been a lot of really great engagement from this panel over the last year and their companies towards defining, where NTP should go. And we're excited to let that planning activity play out. The goal this year is really, from our perspective, to understand what the practical pathways are to testing fuel, testing the reactor, and testing the engine. And demonstrate, and going on towards a demonstration pathway that is again, not on paper. And then, lastly, as vendors participating in the program, this is a monumental challenge for humanity to solve. And I say that, with all the gravity that it deserves. This is one of the most complex technology development efforts that I think we've undertaken. And right now there's probably a bit of, competitive contract structure, which makes sense to really draw out the best in people. But we're hoping over the next year that, we can find better ways to work together, to collaborate and share and do what we do well and let others do what they do well, to provide the most risk reduction to the program. Lastly, just a hope of optimism. I think the renewed focus on NTP, both within NASA and DoD, can really help push this over the finish line after starts and stops over the last 5 decades. And excited to hear what the panel has to say along those lines. So thank you.
Thank you, Ethan. Our next panelist is Russ Joyner from Aerojet Rocketdyne, Advanced Propulsion System Architecture Development. Russ is a fellow for the Advanced Propulsion Architecture Development at Aerojet Rocketdyne. He is a fellow for the American Institute of Aeronautics and Astronautics. Russ has been a primary contributor to the analysis and design of advanced propulsion systems for Aerojet Rocketdyne engineering for more than 42 years. He provides the engineering leadership at Aerojet Rocketdyne for space vehicle propulsion architectural analysis, trajectory and orbital mechanics, and the integration of space and air-breathing propulsion systems. His work with nuclear engines has spanned nearly 35 years and includes the design of the Triton Fast Spectrum Cermet Fuel Bimodal NTP concept. So Russ, thank you.
Thank you, David. I'd first like to thank the organizers of the symposium for this opportunity for all of us to speak up here on this panel. And the idea of using nuclear for rapid transit, I believe, has to be considered from basically what we have to do to travel across the solar system. Going from Earth to anywhere in this solar system is not free. If you're a fan of Robert Heinlein, you know there's an old term that he had in his book, Moon is a Harsh Mistress, called TANSTAFL, and it stood for there ain't no such thing as a free lunch. And basically nuclear helps us deal with that price to move rapidly across the solar system, which we pay in terms of mass, propellant mass. Now I'm striking my tone from used to being a professor. I heard it was a symposium, so I'm gonna have to give you some technical charts here in a minute. So, but that price is discounted with nuclear propulsion. And everybody wants a discount when it comes to paying something. So currently though, and you've already heard what Ethan said, nuclear propulsion is the only technology closest at hand to provide us with that discount. Now let me get into the professor hat side. I want you to focus on this chart relative to what I'm showing you for Earth to Mars missions. And the bottom, each of these, I call them hook charts, bucket charts, but the bottom of each of those buckets is basically the optimum occurrence to go from Earth to Mars over this 15-year cycle that you're seeing. And we've studied different of these scenarios that come about every 2 years, opportunities we call them. And basically you see the 2 trajectory types on the right-hand side, a short stay mission. You see the arc, the blue arc there is pretty much your typical Hohmann transfer. And then you got the curly Q arc, getting you back to catch up with Earth on the red side. And then at the bottom, you've got a long stay mission where you have 2 simple arcs going from Earth to Mars and then the return. Generally, if you can meet the missions that are kind of right there in the middle and designed for the ones that represented by the green lines, you probably can do some pretty rapid missions. So what I want to talk about is this price to pay. Tsiolkovsky back in the early 1900s kind of gave us the tool to understand what it means to, since they've already introduced the idea of specific impulse to your ISP. And ISP is basically miles per gallon, miles per charge. The higher it is, the better. It means it takes less gas to go from point A to point B. And then if you look at those arcs that I brought forward on the graph at the left-hand side from the long stay missions, you'll see there's an opportunity to go fast with nuclear. Those mission types lend you with this high ISP capability to shorten those arcs, which are shown over by the shaded blue and yellow and red curves on the graph to the right. If you want to do the most optimum, which is the lowest velocity change, which was the bottom line of the apex points of those bucket curves on the prior chart, you pretty much are in a slow category, 200 to 270 days, 9 months. Not exactly, something you'd want to expose to astronauts to 9 months each way, zero gravity or near zero gravity, high doses of background radiation, and the psychological implications of being a a person in a capsule for that long. I say capsule, it'll be a little bit better than that. So what you'll see there is in the two curves that I'm showing on the blue plot on the right-hand side, the blue line and the red line. The blue line is a all-chemical LOX hydrogen system that if you want to go better than the slow boat to China, I'll say, you'll see that the mass required in terms of propellant grows quickly. And it starts to go asymptotic at about 7 months or so, 6 to 7 months. And you can't really build anything that can, without it taking many, many launches. And we know some ideas about that when you're doing a chemical approach. Also, the thing to notice on the red line now with the nuclear thermal at 900 seconds, which is a nominal number, 2,700 Kelvin exit temperatures out of the reactor, which is what NASA's targeting for right now in their prototype planning. You'll see the curve from the slow type mission, the big Holman transfer arcs of 9 months. It stays pretty darn flat till you get out to about 4 to 5 months, which means flexibility. That's robustness. That's being able to accept bigger launch windows. And that's pretty good in terms of mission planning and flexibility to a system that you're going to have for deep space that you're going to want to possibly operate over and over again. But the other thing you got to notice is right there as I go on my red bar where it says rapid. When I start getting close to about 9 months, that's pretty good too. I mean, 3 months. 3 months is really cutting down a trip capability. And that's within the scope. If you take and draw a line from the 500 tons on the vertical axis straight across, that's about the size of space station. You know, space station's like 400 tons plus. So we're talking about something that's feasible to build. So if you want to go fast each way, it kind of has a gear effect. So it's a little bit heavier than that, but it's feasible. And that's what nuclear propulsion does. It basically allows us to discount that price with vehicles that we know we can build. Now that is with LOX hydrogen, and the CFM work that NASA is doing is enabling in that direction as well. So we know what it takes to rapidly transit. It's nuclear. I just showed you that. We had kind of proved that out over 20 reactors in the 60s doing the Rover program. That's my favorite article that I always have actually blown up at my desk in my office. And it's from the Chicago Tribune. We had an engine ready, XE prime. You can actually go out there to outside of 4205, I believe, is where XE prime double prime sits, and get a feeling of physically how big that engine was. It was real. And we were only steps away from having one ready to go. We're moving forward. I've got a picture there of a nuclear thermal propulsion system from architectures we've looked at, working with NASA and others. That's a design of a 25,000 pound thrust NTP there, down below it. NASA, under the Space Nuclear Propulsion Program, is working hard with industry and other government agencies to try to make that happen in the near term. So we have to try to support them and make both the DoD efforts and NASA come to fruition. Ultimately, humanity will rapidly cross that new ocean to other worlds, and nuclear propulsion is enabling. Whether it's nuclear thermal propulsion or nuclear electric to go out to the moons of Jupiter, that's what we could. The question is, well, I'll say we had the fortitude to make it happen. I also will say that what we're doing right now is moving the ball down the field. We're getting it towards the goal line. Sometimes it's a grinding running game, no Hail Mary passes, but as long as we're keeping at it, we definitely can make things happen. Thank you for the opportunity.
And thank you, Russ. The next panelist we have is Kate Kelly from BWXT Technologies. She's the Director of Space and Emerging Programs. Kate Kelly is the Director for Space and Emerging Programs of BWXT's Advanced Technologies, leading the strategy and execution of the space and advanced manufacturing portfolio. Prior to her current position, Ms. Kelly was the Advanced Nuclear System Program Manager and worked with project management, quality, and operational excellence within BWXT's Nuclear Operations Group in Lynchburg, Virginia. So thanks, Kate.
Thanks, David. And I'm really glad that I get to go after Russ, so you have that really strong foundation about what NTP is, how it works, and then how we're positioned to take it forward to the finish line. I'm going to talk about some of the key enablers, so get into more specifics about things that have changed over the last 60 years that position us to be able to deploy this technology near term. As David said in the intro, I'm with BWX Technologies. We're a company of 6,600 people. primarily nuclear manufacturing and technology. We're headquartered in Lynchburg, Virginia. And the different businesses that we represent and work in are shown on the slide here. And I show this to start because, one, I know this is an aerospace conference. We are newer to this industry, although we've been involved off and on over the last 60 years as space nuclear has ebbed and flowed of varying levels of interest across the US government. But we have over 75 years of history around nuclear technology and innovation. This includes support of the Canadian commercial nuclear fleet delivering fuel and reactor components. It includes a nuclear medical manufacturing business that's instilling innovation to commercialize new radiopharmaceuticals in Canada currently. And then it includes the largest part of our business, which is the support of the Naval Nuclear Propulsion Program. And so this is a division that delivers 2 to 3 reactor cores to power and the fuel for those cores to power the nuclear navy. And it's something that we've been doing for over 60 years. This is also the business line that delivers research reactor components in the US and abroad, and then the fuel that's needed for those research reactors. So all of these applications are looking at using, all of the space applications we'll talk about are using enriched uranium above what our commercial nuclear fleet uses today. And because of that, you need special infrastructure, expertise, oversight processes to be able to safely and effectively manufacture and deliver these products to the various government customers. We take that infrastructure, take that experience, and then apply it in the division that I represent today, which is BWXT Advanced Technologies. And that's where we are developing new technology for new nuclear applications, taking it from concept to reality. And we have a couple primary focus areas right now, and I'll show those on the next slide. We are developing terrestrial power applications for the Department of Energy and the Department of Defense. So most notably the Scope Pele program, which will deliver, where BWXT will deliver the first nuclear microreactor in the United States in the next couple of years for potential Department of Defense use, providing power to remote places across the world. We also have our space power and propulsion work. So this includes NASA's Fission Surface Power project, which BWXT is thrilled to be partnered with Lockheed Martin on. This is looking at demonstrating a 40 kilowatt electric nuclear power system by the end of this decade. And that's a key enabler to some of the technologies that have been touched on in the introduction. So it's an enabler to scaling up to provide higher power capability on the surface of the moon for all of our commercial and scientific exploration ambitions. But it's also extensible and a key foundation to establishing nuclear electric propulsion at higher power levels as well. And then we have our space propulsion portfolio, which is the support of Jason's program at Marshall and something we've been excited to do over the last 5 years. And that's developing the fuel and fabrication techniques for a nuclear thermal propulsion reactor. And then most recently over the last year, performing along with Ethan and Jerry, their teams in developing the reactor subsystem concepts for these NTP systems. So why now? If space nuclear has been studied for over 60 years, what has changed to help enable these systems to be deployed? I think if anyone is familiar with the NERVA rover program in the 60s, and Russ mentioned this, we built and tested 24 nuclear reactors in various parts of the engine during that time. So if we built and tested that many but haven't flown one, what has changed? And knowing that we're not doing that now with any of these programs, what has changed to position us to be able to deploy this technology in space? And I think succinctly, we've had significant advances in our ability to design and manufacture over the last 60 years. So we can build upon that strong foundation that exists because of the vast operational experience we gained through those test programs, and then continued to gain as nuclear propulsion was studied off and on over the last 60 years, and then apply things like data science and advanced manufacturing to help solve some of the barriers that prevented us from deploying these systems. So first, I'll highlight, so we can use artificial intelligence platforms to optimize our design parameters in our reactor space. So that's coupling all of the aspects of the nuclear, the thermal, the mechanical aspects of our design to narrow in on the best solution given the requirements that we have to be able to design a system that will perform as we need it to meet these aggressive mission objectives. The next is the emergence of model-based system engineering. And this is where it's really important to have a strong aerospace partner because we can use the modeling that BWXT has done around the reactor and apply that to the overall spacecraft. And so working with that expertise, I think on our NTP design work that we're performing with NASA, we're really excited to have Lockheed Martin on our team for that because they bring that expertise that we need to be able to get a look at the entire system. So not just what's happening at the reactor level, not just what's happening at the spacecraft level. And then last are advances in manufacturing. And this is something that has evolved significantly even over the last 6 or so months. I gave a similar talk last year at the Von Braun panel. And so we were talking about how, we were positioned to apply all of the development work that we had done to be able to advance some of the key risks that center around the operating temperatures of the nuclear system. So the fuel has to survive temperatures greater than 2,700 K to be able to achieve over 900 seconds of ISP, which are our current objectives for the various architectures looking at bringing humans to Mars in the next couple decades. And so we're applying advances in our ability to coat fuel, our ability to apply industrial ceramics processes to make the fuel elements that go inside the reactor, and then using unique test capabilities across the industrial complex to be able to test those materials in representative environments. And so as Ethan and Russ alluded to, I think the fuel was the biggest risk and the biggest barrier in the NERVA rover program. And so we've been able to make significant progress to buy down that risk and make this technology viable for demonstration near term. And then last is the utilization of data technologies throughout the manufacturing process. So being able to create digital twins of the parts that we manufacture, comparing those digital twins to what we intended to manufacture, what we intended to design, and verifying that what we have built and delivered will operate as intended and meets the various quality specifications that we needed to. I think I have, these are not related to NTP, but the pictures I have on the slide are representative of just the types of things that the use of data science can help position us to support. So this last slide shows, what the end goal is. So we're talking about developing these concepts at low technology readiness levels, and then rapidly scaling them up across the various TRL scales using infrastructure across, for BWXT, we're using infrastructure across our company or looking across the US industrial base. And so our goal is to take all of these concepts and be able to deliver and produce these systems at scale and over enduring and repetitive quantities. And so the intro, we were instructed to talk about the wonders, the opportunities, and the challenges. I wanted intentionally to focus a lot more on the wonders and opportunities because I think Russ's slide showed it well at the end where, in the 1960s, there was the article that said, nuclear for space is ready. And I want that to be the takeaway. There's enough skepticism around nuclear, and we all know that sending humans to space or getting anything into space for the first time is hard. So the focus should be on the things that have positioned us to be able to deploy this technology near term. With that said, I'll touch on the two things that would help, I think, improve our ability as industry to be able to support these very important missions. The first is the ability to test larger components and more representative components at scale, whether that's ground testing, as Ethan indicated, using subscale ground testing, so not testing the full nuclear system like they did in NERVA, but testing subcomponents of it just to get an understanding of how that system will perform in preparation for a potential flight test. And then the last thing I'd want to touch on is, I think on my second slide, I showed all of the government interest in nuclear, and it's really exciting, and it's building an incredible amount of momentum that is supporting each of these programs. With that, I think government collaboration is and continue to be key to helping support all of the missions that I showed on that slide. So all of the propulsion and power applications for space, coordinating, there's a ton of synergies across them, maybe not in some of the specifics around the technology, but in some of the regulatory and safety concerns that need to be addressed to be able to fly these systems in space. We're all working within finite resources, finite funding, and people to be able to perform on these very important projects. And so collaboration and coordination as we work to advance and mature these systems so that they are ready for space is critical. Look forward to your questions. Thank you.
Thank you, Kate. The next panelist is Gerald Lilienthal from General Atomics. Gerald is the manager of space and nuclear systems at General Atomics Electromagnetic Systems. He has a Bachelor of Science degree in Mechanical Engineering from the University of Wisconsin and a Master of Science in Electrical Engineering from the University of Southern California. He joined Jet Propulsion Laboratory in 1986, where he worked on interplanetary spacecraft, Earth observing science instruments, and space telescopes, Mars rovers, and Mars sampling systems. He is a recipient of the NASA Exceptional Achievement Medal for his work as a program manager for the X-band antenna pointing system of the Space Shuttle's imaging radar. At General Atomics, his contributions are in high-energy lasers, nuclear and energy systems, and serving as a space and science system subject matter expert. He is a program manager for the NASA/INL/DOE NTP contract at General Atomics, which last week was presented its NTP design and architecture successfully to a NASA Department of Energy review panel. So Gerald.
Thank you. I'm recovering from a cold, so my voice is not what I'd like it to be, and you may not recognize it if you've heard me before. So thank you, though. It's really a privilege to be here on this panel. I was asked to join by my NASA management, and it's amazing to me that I have never been to this symposia in all of my 40 years of experience in the NASA community and aerospace community. So it was a thrill to be here beginning on Wednesday. I sat through every session, including the student session in STEM yesterday. I have 5 children. They're all in STEM or graduates of STEM. So we're trying to solve the problem single-handedly, I think. And then the poster sessions yesterday were so great. I really appreciated all of the interest in the various technologies. I'd say about a third of them had to do with nuclear, which was very interesting to see. So what we're doing here today in this panel, I think, is a good part of the future for the NASA program. I agree with the comments that were made about collaboration. I think that the private industry work that's going on with all of the research that's specific to NASA NTP and DARPA NTP can be enhanced by the collaborative nature of the aerospace community. Having worked for 17 years at JPL, that's what I want. That's the vision that I see. now I work for a private company, but I'm inclined to establish good, close working relationships with our brothers and sisters in the other companies. So thank you very much for this opportunity to talk here today. So GAEMS is a company that's been around for a while. We have atomics in our name. It actually started as a real estate company, believe it or not. It's privately owned, and the first foray into the atomics area happened quite some time ago. If you look at the bottom band there, we have a number of reactors that we built. GA actually has the longest standing continuously operating nuclear vendor status. We have the TRIGA, which stands for our Training Research Isotopes and General Atomics Reactor, which was first built in 1958, and it's the most proliferated reactor in the world. We've got 68 of them altogether that have been produced and operate without a single nuclear incident. So we've been in the business for a long time, but it's all been terrestrial, right? There's a big difference between having a reactor on the ground and launching it into space. I know that from my experience. I've launched a lot of stuff into space. It's spread out in the solar system. Things break during the launch process, and the amount of rigor and engineering that has to go into the design of a complex system that has close tolerances so that it works after you launch it is not easy, as Kate has expressed previously. The Nuclear Technology and Materials Division of GA, way over on the right, has well, let me just say, first of all, we have a collaboration with Framatome also to develop a new helium-cooled 50 megawatt electric fast modular reactor concept that's going to produce safe, carbon-free electricity. Can be factory built and then assembled on site. You can see that image there. It seems a little unrealistic that you see something like that in your neighborhood. But these reactors are gas cooled. They don't have any cooling towers, and they're designed to be extremely safe. And so these things might actually proliferate in the future into our common landscape. The work on the rover and NERVA program back in the 1960s, ending at the beginning of 1970 with the cancellation of the program, was crucial. It was an astounding accomplishment that they got as far as they did. They had different regulations at the time for nuclear safety, but their advancements helped put us where we are today. We're building on that early technology, and I wanted to point out to the panel members here and to the audience that the first reactors that fly into space will set a precedent. The things that we do in terms of safety, the things we do in terms of our design will echo down the timeline for decades. And so what we do here is really important. We want to be successful, and I convey my well wishes to all the panel members in their work that they are successful. The fission surface power that Kate Kelly's company won with Lockheed is really important for the future, because we're going to need lots of power, as I mentioned yesterday in one of the panel sessions, for building habitats for humans on the moon, and for doing in situ research or in situ resource utilization work, mining, and other things on near Earth objects and also on the surface of Mars. So we're going to need the power that's generated by nuclear reactors. This is going to be a growing area for the future for the aerospace industry. We've been involved with all those various programs that you see there on the upper bar, but I don't have time to go into all of them. This is kind of a marketing slide, so I apologize if you're offended by that. But one of the things that we do is a lot of internal research and development at GA. We have a philosophy in the company to do advanced research and then be ready when the government comes to us with a need to say, yes, we know how to do that. Here's a demonstrated article. This is the material we'd use. I think we're ready to go into a higher level of engagement with you now in this particular technology. And so GA does that a lot in various technologies, and we're certainly doing that with NTP. We have a robust high temperature materials development program. that's been used and leveraged to win these contracts with NASA and the phase 1 contract with DARPA, Draco. The carbon composites work that we do also has applications in high energy and hypersonic vehicles. But we don't know how to do everything, and we certainly want to partner with good people. So it's my privilege to be here sitting on the panel with Russ Joyner from Aerojet Rocketdyne. They're partnering with us both on Draco, on the Draco phase 1 and hopefully on Draco phase 2, although I don't know if we're going to win that. And and then also with the NASA NTP program. And they're a premier designer and builder of engines. And so a nuclear reactor for NTP does not live in its own environment. We interact with the systems that supply it with hydrogen and the nozzle, which is used to produce the thrust at the exit of the reactor. And so it's important for us to partner with people who really know what they're doing in this area. And so Aerojets are one of our partners in this respect. Systems engineering, I saw a poster yesterday on systems engineering over in the poster session, and I didn't have the privilege of actually talking with the author of that. It was model-based systems engineering and the utility of that for NTP. I encourage all the students in the audience to really focus well on their systems engineering training, because it's an important part of a successful program. When I put together the program for the NASA NTP contract, I made sure that the systems engineering integrated product team was one of the highest funded areas, because I felt it was that important for us to be able to achieve our objectives. And so the EMALS diagram there on the left is an example of that. It's a very highly complex electromagnetic launch system that's used now on the Ford aircraft carriers that GA designed and built, and had huge systems engineering challenges associated with it. And so it can be done, where you have to really do well in systems engineering to do well also with NTP in the future. For our NASA NTP product contract, and I included DOE in that title because both NASA and DOE are sponsoring that. We're building extensively on the Project Rover design, using new techniques for modeling and improved materials to overcome some of the challenges and failures that program experienced during its execution. In order to achieve a 900 ISP, I think the panel members here will agree, you need to have very high exhaust temperature from your reactor. So 2700 K is consistent with a 900 ISP specific impulse. In order to achieve that temperature in a reactor, you're going to have to melt the uranium. And the uranium is going to have to be controlled for where it goes and what it does. And so that's, as Kate mentioned, is key. The fuel development and its function at these high temperatures in the reactor are key to the success of the program. We use high assay low enriched uranium. The Hiroshima bomb used high enriched uranium. The 235U is low enriched and doesn't have weapons grade enrichment. And so it has fewer regulations associated with it. And that's why NASA specified it for our program. But it does make the reactor bigger, and it does make the reactor a little bit more with higher mass. And so that's one of the challenges that you have to overcome. The U-235 also, incidentally, is a lot cheaper to manufacture. It takes a tremendous amount of energy to actually manufacture highly enriched uranium. There's probably more, I think there was more energy that went into the enrichment of the uranium in the Hiroshima bomb than was actually experienced during its detonation. So 235 is easier to get, it's cheaper, and has fewer issues associated with it. Innovative materials that we have developed at GA will prevent the hydrogen erosion failures that were experienced on NERVA rover. And we've actually used more than one fuel type in our reactor. I can't go into the details here, but those types help us to efficiently control the temperatures in the reactor to increase the reliability of the hydrogen as it's flowing through the reactor so that we don't destroy anything on the way. It is scalable to about 1,000 seconds, at least in models, but every model requires a test, and we haven't tested that yet. There's a lot of testing that we have to do. The way you get successful hardware into space is you have good models and you test them and you test them and you test them to make sure you have adequate margins. So let's read this slide from the bottom. We were selected as the sole awardee for Draco Phase 1 Track A. We had the privilege of completing that program. It's a cislunar mission, and we worked closely together with Lockheed and with Blue Origin, which were funded to do the Track B. The Track B portion focused on the spacecraft. Track A focused on the reactor. And right now it's in consideration after proposals were submitted for going into Phase 2. And we hope to hear, all of us hope to hear by the middle of November, I would say, on the outcome of that. The program is very aggressive. It's amazing. So we would have to launch into space by September, well, really by July of 2026, and then demonstrate the mission on orbit, in low Earth orbit, or well, I can't say what orbit it is, by the end of September of 2026. So it's an extremely aggressive timeline for a technology like this. And what's interesting is that because of the unique features of a reactor, an NTP reactor, you can't fire it at full thrust on the Earth like you can with a chemical rocket engine to validate it. So it goes against all of my prior experience, against the test as you fly, fly as you test philosophy for development of hardware. Instead, we'll be able to take the testing up to a certain point and then stop. And then the full qualifiable test is going to be in orbit. So we take it through a cold flow test and a test which brings the reactor into criticality, but doesn't flow any hydrogen through it on the ground. And then we zip it all up and fly it into space. So it's a test article, really. And so it has to be full of sensors. You want to collect as much information as you can on that first mission on its performance in order to help inform the engineering and NASA community on the performance parameters. So it's an experiment in space, and that's something that DARPA is really good at. And I hope that whoever actually wins the contract is successful at this. This is a real turning point for the work. That's about all I have. I think I'm at my 8 minutes. Thanks, Mr. Moderator.
Jason Turpin is our last panel. Jason is the manager of NASA's Space Nuclear Propulsion portfolio and is currently focused on developing and demonstrating nuclear thermal and nuclear electric propulsion systems whose capability can be readily leveraged to support future NASA missions, including crew and cargo transportation to and from Mars. Prior to joining the nuclear propulsion team, he helped stand up NASA's Human Landing System program, HLS. He spent 4 years supporting HLS and served in multiple roles, including the Assistant Program Manager for Sustaining Mission. Mr. Turpin joined NASA in 1999 and spent the first 18 years of his career working liquid propulsion system design development, including managing Marshall Space Flight Center's Liquid Engine Systems branch. His background is in liquid propulsion systems, including reaction control systems, main propulsion systems, and liquid rocket engines. So, Jason.
Hey, thanks, Dave. And thanks, everybody. Good morning. I do have the pleasure of having worked with all of the folks on the panel here as a part of what we're doing at NASA with space nuclear propulsion. So it's been a pleasure working with this group of people and their teams up here in order to kind of advance where we want to go relative to nuclear thermal and move the ball down the field as Russ pointed out. I will not be using my my professor voice because I don't have that. So I did want to start just by briefly kind of giving everybody some perspective on what we think the vision, mission, and our kind of ultimate objective is in the NASA Space Nuclear Propulsion program and project. Ultimately, at NASA, we want robust and enduring access to destinations throughout the solar system. So I would call that our vision, our desired future state of really where we want to be. We want to be able to move effectively, efficiently, and robustly anywhere throughout the solar system. If you translate that down to a mission, what we want to do in order to achieve that desired future state someday is to revolutionize space travel through the development and demonstration of robust and high-performing nuclear propulsion systems. So we think that, you know, it's been discussed here, nuclear propulsion is a keystone into moving into that next level of performance that will allow us to really efficiently and rapidly move throughout the solar system for commercial interests, for civil space, and for defense. I think all of the above. So within the program itself, what we're specifically doing in order to kind of accomplish that mission and ultimately that vision is we are tasked with developing and demonstrating nuclear thermal propulsion and nuclear electric propulsion systems whose capability can be directly leveraged or readily evolved for NASA's future missions, including both crewed and large cargo Mars missions. And so if we kind of keep our eye on the prize in terms of the Artemis program and Moon to Mars and where we want to go from our NASA perspective, you know, the semi near term to moderate focus is really how do we get to Mars? And so a lot of the requirements that we come up with and a lot of things that we do in order to address technology needs are driven with that look towards Mars for nuclear thermal propulsion. But we are taking a step back and also beginning to really look at applications for cislunar space, for near Earth and cislunar opportunities for both commercial and NASA. You know, NASA interest, especially since it's been mentioned here, there's a lot of interest out there today for that area and those mission spaces. And we'll talk a little bit about that as we move forward here. So within space nuclear propulsion, specifically at NASA, this program, you know, like I said, our objectives are really focused on moving the ball down the field for nuclear thermal and nuclear electric. So that's what, you know, our kind of narrow focus is in that space. And what we really want to get to is an integrated system demo for both applications that's meaningful and evolvable to ultimately where we want to get to for Mars and in other mission spaces. So we're focused on NTP and NEP, and I think, you know, we've had some discussion about that already. Nuclear thermal is really nice because it provides, you know, double or more than double with lots of headroom and growth potential to go beyond that. Relative to what's traditionally done in the chemical space, which is really nice. And you can do that. You can get that miles per gallon or that ISP for those systems at thrust levels that are meaningful in terms of, you know, changing orbits rapidly or transiting rapidly to Mars or other places, because you can work up to fairly high thrust levels with these systems, which is nice. On the flip side of that, the nuclear electric side, you get really high efficiency in terms of the amount of propellant you got to carry to go get a given delta V, but you're a little bit restricted in terms of overall stage thrust that you can do with those systems by themselves. And so the way we kind of approach it, especially for Mars missions, is we look at what nuclear and thermal can do in order for crewed and cargo Mars transit. But when we talk about NEP, we usually strap an NEP system with some type of hybrid chem system in order to get that higher thrust to make those missions more doable, at least in the near term. Something that's common between both of these segments for us is, has already been mentioned, we're really focused on HALEU, this low enriched uranium fuel for doing these missions. There's all kinds of positive reasons for that in terms of, you know, proliferation risk and what it takes to handle and store the material, and also how it plays forward in terms of where industry wants to go for small modular reactors in the future and other things. So there's a lot of common threads through HALEU. And so I think that's a really good thing that we're all doing as a community on the government side and on the industry side, which is fantastic. I would say for nuclear thermal, really the top risk is how do you design the fuel in the reactor? When you get down to the engine specifically, how do you design the engine in the reactor to drive to say some type of 900-second ISP performance for a hydrogen setup? It really forces that extreme environment that's been mentioned, fuel temperatures, really high fuel temperatures, and really challenging reactor design constraints. And so there's a lot of risk and development to be done there if you want to set your requirements at that point. Now, if you're willing to back your requirements off a little bit, things start to get easier, and it's a little bit of a different conversation. On the NEP side of the house, you don't have to run that reactor as hot, and so there are different challenges there. Although there are still challenges with reactor design and development and fuel work, it's really more about how do you do power conversion and power management? How do you handle all the waste heat? How do you take what you're getting out of that thermal reactor and effectively and efficiently converting it to what you can use to drive these high power electric NEP engines? And so we're involved in both of those things within space nuclear propulsion. So I think historically, at least I would say maybe over the last couple of years, and I'm a little bit new to the project, so I'm still learning, but our focus has really been at NASA more on what does it take to get to these Mars missions, to do large Mars cargo missions and crew transit missions, and how do we come up with requirements and come up with development opportunities to go do that. But I think recently we've really begun to transition to see a lot of benefit from moving into and thinking about what can be done in terms of Earth orbit and cislunar space. And there's a lot of interest out there from a lot of people. So we're shifting our focus to kind of include those things. And I think there's a lot of near-term interest there and pool that's relevant today. And then that's also a great proving ground to kind of evolve these systems for going to Mars and deep space and other places. So we're interested in all of the above, and the reactor contracts that have been mentioned up here a couple of times. We're currently, as a part of kind of moving the ball down the field here, we've got reactor contracts with GA, BWXT, and USNC all today working kind of conceptual early preliminary design work for what a nuclear thermal propulsion reactor would look like. And we just finished our phase 1 work where these folks came in and they presented, 30% design review results. And so we've been making good progress, and we hope to continue to make good progress there. I think the last thing I would want to leave you with is and the panel here has done a really good job, I think, about talking about the importance of what it takes to integrate these complex systems. And it's really easy when you get into this nuclear space to start thinking about all the challenges associated with fuels and materials and reactor development. And I certainly don't want to minimize those challenges, because they are challenging, especially where we're trying to drive the requirements in the mission spaces that we're doing. But I also think it's important to recognize that, as has always been true, the whole is greater than the sum of the parts when you talk about engineering complex systems. And that's even true for nuclear propulsion systems. So this is, when I first started working at NASA, one of my mentors gave this to me, and I thought this thing's probably been around since the 60s, this cartoon, but I think it does a really good job of just kind of showing and kind of emphasizing that point. So if you look at that top left diagram, that would be what a engine system or a rocket engine would look like if you were only worried about performance and the performance analyst was doing the design. It would basically be all nozzle and nothing else. And if the turbo pump folks were doing the design, it would be all turbo pumps and nothing else. And the next one to the right is the marketing team, or what we might call business development. And I'm not hating on business development. I do business development myself, but you kind of take an old engine and slap some duct tape on it and say this engine is certified for humans, and it can do anything. So I think we really got to take a step back and look holistically at what we want these propulsion systems to do, and ultimately how they integrate in the stage of the vehicle they're going to fly in, and take a step back there, and then ultimately take a step back for the missions that we want to do, and just keep that perspective in mind while we are working and focusing on, these challenges, these deep technical challenges in terms of fuel and materials and other things. That's all I had there.
We have time for any questions, or we 5 minutes? All right, so let me start off by a question here real quick. Jason, and I'll pick on you right off the bat. All of our panelists have identified collaboration, particularly across the government, as something that's important to kind of push NTP across the finish line. What are we doing in collaboration?
Yeah, I think that's a great point, and I think several folks mentioned it here as we move down the line. But doing something like this is really an all hands on deck effort. If you really want to go develop these systems that are really, really game changing capability kind of systems within the funding constraints and the environment that exists today, in order to go do it, it really is an all hands on deck a setup. And so it's certainly on the government side, we've got to be willing to get our act together and partner and collaborate in a way that we're not pulling everybody in different directions, and where can we get on the same page in terms of what we want to do, and where the Venn diagram overlap is of requirements, and where we want to move the ball down the field. So particularly on the NASA side, we're working heavily with DOE. In fact, our reactor contract work that we're doing with these folks is through DOE in order to go do those contracts. And so we're doing reactor development and fundamental fuel and materials development with DOE. And so they're a big time partnership with us in terms of what we're doing. We're also partnered with DOD. We're partnered with a couple agencies in DOD. We're doing work with DARPA, collaborative work with DARPA in terms of what they're doing for DARPA Draco. And that was mentioned a couple times up here too. So DARPA is working to really go do a flight demonstration nuclear thermal propulsion system really rapidly. That's kind of their objective. And so we've been helping them and working with them on that. We've also been working with the Strategic Capabilities Office, for instance, in DOD doing fuel development. So I think we're doing those things. I think probably the next step and the real all hands on deck effort is, can we find enough synergy to get around kind of partnering together and really moving forward for some big demonstration or something else down there to really make a difference?
Thank you, Jason. Our question.
Hello, I'm Thais Arslanbekov. I'm an undergrad here at UH, and I was wondering, how are y'all currently working to optimize lower thrust to weight ratios associated with NTP and shielding and other radiation associated risks? Thank you.
Kelly, do you want to take that? I'm sorry, Kate.
It's
do you want to
okay.
take that? Give me.
Yeah, I'll take a first cut at that. And so I think it really ties back to the materials. So being able to, well, materials and design. So first looking at what the optimum configuration is to be able to reduce the thrust to weight. So being able to evaluate using AI to evaluate, dozens of parameters at a given time to narrow in on the best solution. So that's one way from a design space. And then again, the advances in manufacturing, I think, make that real. So being able to manufacture and incorporate more complex high temperature materials or lower mass materials into our reactor concepts. And then most importantly, being able to test those new materials in representative configurations to help validate that we can in fact achieve, the objectives that we've set through our design analysis.
Thank you, Kate.
So I have one additional quick answer question, please, from online. Any thought on operations and maintenance of nuclear reactors on the moon? What about qualifying technician astronauts?
Okay,
Can I?
sure.
Yeah.
Yes, Kate, go ahead.
I have two ideas. So the first is, I think there's a ton of synergy between, for especially a fission surface power system. I know we spent a lot of time talking about propulsion, but a fission surface power system, so that's operating on the surface of the moon. We operate reactors in remote places. We've been doing it for the last 60 years through our Navy's submarines and aircraft carriers. And so there's a robust training and qualification program for the operation and maintenance of those nuclear reactors. And then there's also a huge synergy that we can pull from in our heritage spacecraft work that's ongoing today, but then also the terrestrial nuclear industry that we have a ton of operating experience that we could pull from to be able to come up with a solution. But I'm interested to hear what our other panelists might have.
Well, I just feel compelled to, if anyone here has not seen season 3, episode 1 of For All Mankind, it starts with an NTP engine ground test where the ground is the moon. And so, just to bring that up too, that, as kind of a joke, but we talked about the challenges of ground testing a full engine on the ground. Obviously, it's a little bit different atmospheric and population dose considerations on the moon. So felt the need with that question to bring that on. But in general, on orbit maintenance of NTP systems, similar to higher thrust to weight ratios, are things that we really think of as the second generation. And certainly this panel, this program, very focused on first generation. It's more than just the technology; it's the system that's system that supplies it, builds it, tests it. So,
Thank you, Ethan.
All right, so thank you very much, panel. We appreciate it and got some great depth there.